Welcome to this pre-recording of a talk on computing nearest singularities and solutions of polynomial systems. So this talk is a contributed talk in the conference on applied linear algebra in the session on randomized method and polynomial systems. So I will explain the problem in 3 slides, starting with the theorem of Fabry, indicating why multiple double precision might be needed. And then, most relevant for a conference on applied linear algebra, the main part in the computation is actually the solving of a triangular block Toeplitz system. So that's the first part of this presentation. In the second part, I will give an example of a homotopy leading to a singular convergence, leading to a singular solution. And if we encounter a singular solution, we can detect it with the theorem of Fabry, but we will also observe a very slow convergence, typically a logarithmic convergence. Numerically, one can run into troubles when one is already very close to a singularity. One actually has to recondition the homotopy in order for the numbers in the coefficients of the Taylor series, in order for those numbers to be well scaled. So, and I will end by pointing at some free and open source software. And essentially the purpose of this talk is that you would look into our papers. Okay, so a homotopy is a family of systems, typically in one parameter, which we call t. T you could see for time. So this family of systems, so this homotopy defines solution paths. And they are parameterized in T. So the homotopy itself is a very nice transition between polynomials. But the solution paths actually can be very, very complicated. But the essence is that they are analytic. So we can compute a Taylor series, because we start always at regular solutions. So in some sense, this is on analytic continuation, in particular numerical analytic continuation. And the central theorem, at least for this presentation, is the ratio theorem of Fabry. If you have a Taylor series and all the coefficients are non-zero, so the ratio is well defined, and if there is this limit, then the limit is actually the nearest singular point. And actually it lies on the boundary of the circle of convergence of the series. So this is very important in step size control, so that you can adjust your step size, your increment in t. It's also very important where you can apply Newton's method. And here actually we will apply it when we approach a singular solution. So we can detect a singular solution. So the ratio theorem itself has a very nice formulation, a very useful theorem. The proof is complicated, but you can get to it, you can get to recognize the truth of the theorem if you construct a Padé approximant with a linear denominator. So in the denominator you can't, so there's an approximant in t. When the denominator is 0, that is actually the ratio. So solutions at infinity and single solutions, they are just as difficult and complicated. Why do you need multiple double precision or double precision in general? So multiple double arithmetic is an extension of double arithmetic. So if you have two doubles, a double-double, then the first double is a regular, the leading part. and the second double can be interpreted as the error on the first double. So if you compute less than 7, so when we do the path tracking, the default is actually 8 terms. So then everything goes in double precision. But if you start to need more and more terms, and here I'm using the nice exponential as an example. So just to represent the last coefficient accurately, and actually when we do the Fabry, when we apply the Fabry ratio theorem, we are looking at the last coefficient, so they need to be quite accurate. So you need that precision here. So I've been also using GPU computing. I can go with the GPUs up to octodouble precision. The hexadecimal hexadouble precision is still a work in progress. So this is why this table has the word need in there. So I've been using the QDlib, and also more recently extended this to octodouble precision, decadouble precision, hexadouble precision with the Campari library. Here is another important concept. So this is still part of the problem. In some sense, I got the idea for linearization. So backing up a little bit, if we run Newton's method, we solve a linear system to compute the update. So Newton's method is used to compute the terms in this Taylor series. So you can look at this as a matrix of power series, but linearization is looking at a series where the coefficients are matrices. And you solve for vectors, not vectors of power series, but actually you solve for series where the coefficients are vectors. So this is an important idea, and I got to this idea by going to the 2016 conference on linear algebra. It was in Belgium, Leuven. So you see the structure of this triangular block Toeplitz system. So what is on the diagonal is the Jacobian matrix. So just the classical Jacobian matrix if you would be running Newton's method on a nonlinear system. So another way to see why you might need multiple double precision or multi-precision in general, here we are solving a linear system in each step. So we first compute the leading coefficients, x naught, and then we compute the next vector of coefficients, x1, modifying the right-hand side b1, subtracting a1 times b naught. a1 times x naught times. So what I want to indicate here, and the slide is very sparse, what I want to indicate, if in every of these back substitutions you would lose 2 decimal places, then you might already lose 8 decimal places when you get to the last block of coefficients. It's fine if if everything is well conditioned and you'll be working with Taylor series. But imagine if you work with 32 coefficients, and we often need those if we approach a singularity, then you need again multi-precision. Okay, so this is the first part of my talk. Here is an example. I define the homotopy as a system of polynomial systems in one parameter. And here you see 2 polynomial systems, one that is very simple, that you can solve, and then also a simple polynomial system, by the way, it has to fit on the slide, where there is a triple root. So at t equals 0, you start at 1, 1 as one of the roots. And then at t equals 1, you follow the paths, and the paths are shown here in the complex plane. You end up at 1, 2 for 3 of the 4 paths. The session is on randomized method, so there is this random complex constant gamma. This ensures that the singularities only appear at the very end, so we have no singularities in between. What you see on the plots here, the red is the trajectory of the solution curve. So we start with x at 1 and actually we turn back. So the reason why these paths are so curved may have to do with this random gamma constant as well. The random gamma constant makes that the paths actually will not run into singularities. Equally important are these disks. So I mentioned the disks of convergence. So they are representative of these disks of convergence of the Fabry ratio. Only that they are half of the size. Typically, we actually don't want to run into any singularities. They are at the boundary of the Fabry circles, but we take half of them. So you see that in the middle of the path, these circles can be very large. So the paths actually, they are continuously, but here you see a line segment. So each time we compute the radius of convergence, and you can make a plot like was done here with the software. As we are going to a triple root, and we are often still very far from t equals 1, but you can see the radii are actually getting smaller and smaller. It's specifically small in the x, but here you see also in the y coordinates that we go to 2. 2 is actually still far away on this plot here, but the circles, you can already see that they are getting smaller as we are taking half of the radius of convergence. Logarithmic convergence, by the way, is very small. We are used to running Newton's method, one step, and we have twice the number of correct decimal places. Logarithmic is the opposite. You may have to do twice the number of work for one extra bit of accuracy. I was also saying that you have to get very close. So although it depends what your scale is, so at t very close to 1, we actually see that the ratio theorem of Fabry detects the singularity at the end. So the nearest pole is actually 1 then. Look at the imaginary part, 10 to the power minus 8. Very tiny. This is actually the situation at the right here. Before that, when t naught is less than this t star, we have this pole rho, which is the last. The situation in the middle is a very special situation where you are at equal distance of rho and 1. And that situation causes the theorem of Fabry to be confused. Also, extrapolation doesn't work anymore. We wrote a paper on this. But the point of the slide is the reconditioning of the homotopy. So notice that the t naught here is actually the 0.9999684, and you should rescale that with Taylor series. We always start at 0, and our next point is 1. So this is what this reconditioning actually does here. If you do not do this, you are very close. So 10 to the power minus 4 is actually the radius of convergence here. And that is way too small. You're going to have huge numbers showing up. Okay, I'm at 15 minutes now, and that's the absolute total maximum. I'm not expecting questions. when I do the pre-recording. Our software is free and open source, so free at GitHub. It's Python, the Python interface to PHCPack now runs on Windows native, also on Linux, on Mac, and typically you can run this in the kernel of a Jupyter notebook and then make the plots. So I mentioned the block Toeplitz structure of the matrices. So this goes back to joint work with Nathan Bliss, where we worked out the method of Gauss-Newton to compute the power series. We discovered the theorem of Fabry when jointly with Simon Thelen and Mark van Baarle we were making a robust numerical path tracker. Robust means that the path tracker is less sensitive to tolerances. So because we have an a priori step size control. The reconditioning idea and the construction before around it arose with work with Kailash Viswanathan, the 2022 paper here. Okay, for me, I have 12 minutes time and I'm going to deliver this talk. So I went way over time. But I hope that this video will be useful.